Good afternoon, everyone. My name is Ilona Ylivinkka. I'm a PhD student at the University of Helsinki, Inara. And I was asked to tell you something about the measurements of the research done at MODEST station. So we'll start with that. I will introduce something related to that, and then about the linkages between the biosphere and atmosphere. And then there's something about what is my contribution to that research. And as you are not able to come or weren't able to come here, I tried to add a lot of nice figures or pictures from HyytiÄ, so you can enjoy them. So I'm working at MODEST station, and we do measurements from a boreal forest, which is shown in green, this boreal forest shown in this map. And boreal forests are the world's largest forest area, and they make something like 15% of world's land area. So the research done in this area is very important, and like even doing research on climate and climate change. So what are our research questions actually? So we want to know how climate affects structure and functioning of the ecosystem, what is natural variability, and how is climate change affecting these processes. And then on the other hand, how does ecosystems affect climate? So there is, for example, carbon, nitrogen, and water cycles, the synthesis of reactive compounds, also known as VOCs, volatile organic compounds. And then there's, for example, albedo effect. So when there's less snow in wintertime, the albedo of the forest is smaller, and then less radiation is scattered back to space, which then enhances the climate change. And then one topic which I'm going to talk to you more now is that how does the biogeochemical cycles link the ecosystems and the atmosphere? So how do we then answer these research questions? So we do measurements. We want to measure atmosphere, so all the trace gases, the aerosol particles in the atmosphere, and then basic meteorological variables. So for example, how much water is evaporated and how much is precipitated into the forest. How does the gas fluxes go? What kind of chemical reactions there are in the atmosphere? So everything that's in the atmosphere. Then we want to measure forest. So we know what kind of trees we have. We know what are the emissions, how much we have biomass, how much the trees grow, and the level of photosynthesis and gas exchange. So all those variables that relate to forest. Then we do also measurements from the soil. So again, gas exchange. We measure litter fall, basic like soil temperature and soil moisture. So all these processes that relate to biological activity and water budget, for example. Then we have measurements from lake. We can measure, for example, CO2 concentration, temperature profile, heat transfer, and such things. And then we also have similar measurements from the Peatland measurement site. So this is the whole picture. So we want to know all the matter and energy flows in our ecosystem, and what are the interactions and feedbacks between the atmosphere and the ecosystem. So what is the research? So we do long-term comprehensive measurements because we want to know the physical, physiological, and ecological, understand the processes. And then we can also do some modeling. So that is also needed to describe and understand the processes. We want to know the long-term dynamics, and we also have winter. So there is freezing temperatures, snow is covering the forest. So we want to know what is happening in the winter time. And then we also need modeling for scaling or extrapolation of our results. So we can, for example, measure gas exchange in shoot level from one shoot. Then we can do it in canopy level from this kind of high mass that we have here. And then when we combine, for example, our measurements from other research stations and use some modeling, we can get some estimate, for example, what is the carbon sink of the boreal forest. And then also when we have these long-term measurements, we can do some management experiments. So for example, last winter, forest was harvested, so some of the trees were cut. So now we can do data analysis and see how that affected, for example, photosynthesis, or is there now more radiation penetrating inside the canopy. So all this is possible when we have all these measurements. And then we can also do some laboratory experiments. So as you notice that our research is really multidisciplinary. So we need biology, forest sciences, chemistry, atmospheric sciences, mathematics, engineering sciences, and data sciences, as for example. So I'm sure that no matter what is your background, there's something that you can add here. And also, as Hanna said earlier, that there's also this art projects. So not only like hardcore research. So if we now go further into the interactions between the forest and the atmosphere. So this is the climate feedback loop that Kulmala et al. Introduced in 2013. It might look a little bit difficult, but I will explain this to you. So we have increased CO2 emissions or concentrations due to anthropogenic emissions, and that makes the forest more active because there's more CO2 that they can take from the atmosphere. And that, of course, reduces the CO2 concentration in the atmosphere. So when the forest photosynthesize, they also produce these reactive gases or volatile organic compounds. And some of those compounds can contribute to the formation of secondary organic aerosols or new particle formation. And when there's more particles in the air, they scatter solar radiation, so the share of diffuse radiation becomes larger. And it has also been shown that forests can photosynthesize more effectively when there's more diffuse radiation. So this is a study from Esova et al. 2018. So this blue line is from Smertu station. So this is diffuse radiation to global radiation, and this is a measure of photosynthesis. So we can see that at certain level of diffuse radiation, the photosynthesis is most effective. So when the photosynthesis is effective, then again, there's more VOCs and so on. And then the other half of the loop is that when there's more CO2 in the atmosphere, it increases the temperature, which also increases the emissions of the reactive compounds. And there's aerosols, and some of those aerosols can act as cloud condensation nuclei. So inside every cloud droplet, there is an aerosol particle on top of which the water is condensed. And when there is more cloud condensation nuclei, then there can be more cloud droplets. And clouds also affect radiation, so that decreases the temperature. So this is the idea how ecosystem and atmosphere can interact. And now if we go further into these aerosols, I will just quickly show that for new particle formation we need usually at least sulfuric acid, amines, some organic compounds, so those reactive compounds that I was talking about. So what I have been doing is that we developed this kind of sulfuric acid proxy, because even though sulfuric acid is important for new particle formation, it's not measured everywhere, and there's of course gaps in the measurement data and so on. So this Peatland et al. 2009 proxy has been used a lot. So this Peatland proxy is shown with this red dashed line here, and the measurement data is with blue line. So we can see that it's okay, but it's not a perfect proxy for sulfuric acid concentration in the atmosphere. So what we did is that we added one source term and one more sink term in this Peatland proxy. So we got a better idea how this sulfuric acid is formed in the atmosphere, or what is the concentration of sulfuric acid. So this is, we did several fits, but this pink is this pink here, and we can see that they go now quite nicely with the measurements. So this is something that we can do from the measurement data. Then something else that I have been doing is developing an algorithm for cloud type classification. So previously we didn't have any idea basically what kind of clouds we have in HyytiÄ, even though it's very important for this these interactions. For example, different kind of clouds or the cloud type affects how it's affecting the temperature. And also clouds can scatter radiation and cause diffuse radiation, similar to aerosol particles. And then, for example, this Data et al. 2017 paper, they showed that new particle formation usually happens when there's a clear sky, but they used only a parameter to describe whether it's a clear sky or cloudy sky. But what we noticed is that even though this parameter shows a clear sky conditions, there can still be clouds. So now we want to investigate more on how these different color types affect, for example, new particle formation. So this is a pie chart of different cloud types when a new particle formation event started. So this yellow shows that usually new particle formation happened when there was a clear sky or some light cirrus clouds. Or then quite often there could be also some fair weather cumulus clouds. But on the other hand, when the event did not happen, there was quite often stratus or stratocumulus, so those gray and miserable overcasting clouds. So this is quite what we expected, but now we can go further into this. So this is something that is to come. It's not ready yet. And I would like to conclude with a take-home message. So if we want to gain comprehensive understanding, we also need comprehensive measurements and long-term measurements. And the research is really multidisciplinary. So here are my references, and thanks a lot for your attention.
Thank you, Ilona. So during this year, of course, well, in May it was not possible to organize face-to-face meeting, but we have been planning also to have like almost half of a day, several hours excursion, visiting different research facilities and talking with students who are actively working at the HyytiÄ research station. In particular, Ilona is one of the PhD students who is actively involved in such kind of activities. And we hope that in a face-to-face meeting, you will have more opportunities to talk with a lot of researchers, including the younger generation.